Let's talk about RC equations. This refers to a combination of two circuit elements. One is the resistor and the other is a capacitor. There are two kinds of circuits we will be studying. One is called the RC discharge circuit, where you take a capacitor that's fully charged and let it simply waste all its stored energy by sending current through a resistor. And when it does that, resistor dissipates energy. That's its only purpose in life, as power dissipated through either a bulb or just heat. So if you think of the battery as having a plus and a minus sign, it would send current through the circuit. Basically what's happening is the negative charges are getting moved to the positive plate, and eventually the plates become neutral. So that's the mechanism of discharge. In the second video, 7b, we'll also be studying how the capacitor got charged in the first place, and that is due to the charging circuit, where you put the capacitor in series with a resistor and a battery. Now you may wonder, why even have this resistor for the charging circuit? Why not simply connect the capacitor to the battery? If you tried that in real life, you'll find that the capacitor will explode because the rate of change of charge is too high, and the capacitor undergoes what's called dielectric breakdown, and it starts smoking and creating a bad electrical smell. So you don't ever want to do that. Always use a current limiting resistor in series with a capacitor while charging it. But once fully charged, this capacitor can now be isolated or this battery removed, and the capacitor's energy, when required, can be discharged through a resistor. This is the reason why you have a big capacitor in every amplifier of a stereo system. The capacitor is always charged, and whenever the speakers, which would be the resistor here, require a big dose of power, then the capacitor discharges for creating music. So let's go ahead and analyze this. Current is going to flow in this circuit, so we can write by the KVL. We can write the voltage across the capacitor plus the voltage across the resistor must be equal to 0, because KVL says the sum of all the voltages across the circuit must be equal to 0. So the voltage across the capacitor is just equal to, remember the definition of capacitance is equal to charge over the voltage. So voltage is equal to charge divided by the capacitance. So that's going to give me Q over C. And the reason I put a lowercase q instead of uppercase Q is because I know this charge is going to change with time. As the capacitor keeps discharging, this charge is going to keep changing. And my convention is always to use lowercase q and lowercase I in case of the current. So I get this equation. Now this is what's called generally speaking, a differential equation, because current I is dq by dt. The very nature of the definition of current is that it's the rate of change of charge. So if I do that, I get q over c plus r dq by dt equals 0. Now this is not a difficult differential equation at all. In fact, it's a clear case of separation of variables. So what I'll do is I'll move everything to the other side. So I'll get, let me go to this side. So I'll get dq by dt is equal to negative 1 over RC, because I'm taking the R also to the other side, times Q. Now if you notice the left hand side, it has dimensions of coulombs per second. The right hand side therefore should also have the same dimensions. Q is already coulombs, therefore the product of R times C must be seconds. So the units of R times C are the units of seconds. For this reason, the product R times C is known as the time constant of the RC circuit, denoted by the Greek letter tau. Later on we'll see what the true meaning of the time constant is, but right now you can just imagine it to be some shorthand notation for R times C with the same units as time, namely seconds. So once we can have the time constant, we can replace RC with the time constant. So I have the differential equation dq by dt equals minus q over tau. Now this equation is amenable to what's called separation of variables. So what I do is I take all the q things to one side. So that's dq by q, and all the t things to the other side. That's minus 1 over tau dt. And at this point, I can integrate both sides. So I'm going to get, if I integrate the left side, I'm going to get the natural log. So I get natural log of q is equal to minus, and that's just going to be t over tau, plus some constant of integration. Now because C has already been used for capacitors, I'm going to just write the constant out fully. How do you determine this constant? Well, you have to put some initial condition, and that initial condition is that at time t equals 0, the capacitor had a certain charge. So cap's charge, q of 0, was something. Let's call it q naught. Now I use a capital letter because that's a constant. So I can substitute this into my initial conditions. ln q equals times 0, so that's going to be negative 0 over tau plus constant. And this tells me that the constant is just natural log of q naught. Once I've determined the constant, I can put it back in the solution to the equation. So I get natural log of q equals minus t over tau plus natural log of q naught. Now I can bring the natural logs to one side. So that gives me natural log of q minus natural log of q naught equals negative t over tau. And natural logs have the property that the difference of natural logs is a ratio. So I can write this as natural log of q over q naught is equal to minus t over tau. Almost done. I just have to take the exponential of both sides. So this tells me that the charge as a function of time is equal to q naught e to the minus t over tau. Well, strictly speaking, I should have done one more step here. So maybe I should go ahead and do that. I'll get q over q naught equals e to the minus t over tau, having taken the exponentials of both sides, and then I multiply both sides by q naught. So that's my main equation for the charge as a function of time. It changes as an exponential decay. Once you have the charge as a function of time, you have everything else, because the capacitor's voltage can be found by just doing q over c. So the capacitor's voltage as a function of time, let me call this Vc as a function of time, will just be q over c. So that's going to be q naught over c e to the minus t over tau. And then the voltage of the resistor is given by that first equation, which tells me Vr is always negative Vc. So that also can be found because you know what Vc is. The current through the resistor can be found by using I equals dq by dt. So that's the next thing we'll do. I of t equals dq by dt. And that's going to be negative because I differentiated, I pulled down the negative sign from the exponent. So that's negative q naught over tau, which is r times c. So I'll write r times c e to the minus t over tau. Now if I expand this out, Vr is minus Vc and Vc is all that. So that's going to be q naught over c e to the minus t over tau. I recognize that q naught over c e to the minus t over tau with a negative sign is none other than Vr. So I'm going to write that as actually, you know what? I'm just going to take negative q naught over c and write this part without the negative sign, I'll write this as VR naught, the initial voltage. So that's going to be negative VR naught over R e to the minus t over tau. And I'm going to call VR naught over R the initial current. So that's minus I naught e to the minus t over tau. Now this minus sign is really interesting. It means that mathematics actually correctly recognizes that charge movement is occurring due to the negative sign charges going from the negative plate to the positive plate. Okay, in other words, the movement of electrons. But we are considering the Benjamin Franklin convention of current as being the movement of positive charges. So we're going to take the current to be in this direction, even though it's really obvious that what's really happening is the negative charges are going in this direction and neutralizing the positive plate. And that's the reason for the negative sign. So we're going to remove the negative sign and think of the conventional current I of t as just being equal to I naught e to the minus t over tau. So those are the various equations of the RC circuit. These equations are all well and good, but it's better to just remember them in terms of a plot. So if I try plotting them, what will I see? Let me try doing the current first, the charge first, and then I'll tell you about the rest. So Q as a function of time. Let's plot in the units of time constant. 1 time constant, 2 time constants, 3 time constants, and so on. It's going to start off with some initial charge Q naught at time 0. Now how does it go as time progresses? Well, at t equals tau, I'm going to get Q of tau is going to be Q naught e to the power minus 1. Now if you take a calculator and calculate e to the power minus 1, it's approximately 0.37. So this is going to be 37% of Q naught. And if you take Q of 2 time constants, it's going to be 37% of 37%. So it's going to keep falling down by 37% of the previous value after every time. So if I try to freehand this, I'm going to get something like this. It's going to quickly go down to 0. I mean, technically it never does, because t has to go to infinity for this to go to 0 because of the nature of the exponential graph. But in the notes, I show you that there's a concept called practical discharging, where we find the time taken for this Q to go down to the charge of a single electron. Once a single electron is left on this plate and a single positive charge on that plate, there's nothing you can do. You cannot transfer a fraction of an electron from one plate to the other plate, and so that's when discharging practically stops. Now all the other graphs look kind of like this, so I won't bother drawing them. The current graph, the conventional current graph, the electron current graph looks like that. It goes like this. But the conventional current graph goes just like that, with the initial current I naught replacing Q naught. And the capacitor voltage graph also looks the same as this, except with the initial voltage across the capacitor, which I'll call VC naught in place of Q naught there. And the resistor's voltage is the opposite of the capacitor's voltage, so it will look like that. So maybe it's worth drawing the capacitor voltage and the resistor voltage. So in the same graph, so it also represents voltage, I have the capacitor voltage VC, and the resistor voltage comes up to meet it, and so that's going to be VR naught. And you can clearly see that VC naught and VR naught are opposite each other, and at any given time the total voltage will always add to be 0 as required by the principle of KVL.